You have been lied to your entire life. Not maliciously, not on purpose, but every single time you sat in a classroom, every time you opened a textbook, every time you watched a documentary about our solar system, there was something missing, something enormous, something that changes everything about how you understand where you are in this universe. You know the picture. You have seen it 1,000 times. The sun sits in the center. The planets stretch outward in a neat line. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Everything arranged flat, like coins on a table, like a map drawn by someone who had never actually looked up. That picture has lived inside your head since you were a child. And for most people, it never gets questioned. But today, we are asking the question that almost nobody asks. What is above that picture? What is below it? When you look at that flat diagram and imagine flying a spaceship straight up, perpendicular to all those orbits, what do you actually find? The answer is not what you expect. And by the time this is over, that childhood picture in your head is going to be gone forever, replaced by something so much bigger, so much stranger, and so much more beautiful that you will never look at the night sky the same way again. The solar system is not flat. It never was. And above it and below it, stretching in every direction for more than a light year, is a structure so vast it makes the entire realm of the planets look like a single grain of sand on an infinite beach. This is the full story of what actually surrounds us. Let's begin somewhere that feels familiar. You are standing outside on a clear night. You look up. You see stars. Hundreds of them if you are somewhere dark, thousands if you have good eyes and a dark enough sky. And somewhere up there, invisible but real, is the sun's family of planets, all circling in their great ellipses, all keeping roughly to that famous flat disk, that ecliptic plane you were taught about. The question that almost nobody asks is this: why is the solar system flat in the first place? Because it was not always flat. There was a time, about 4,600,000,000 years ago, when there was no solar system at all. No sun, no planets, no Earth, just a cloud. Imagine a cloud of gas and dust so enormous that it stretched across several light years of space. Mostly hydrogen and helium, the two simplest elements, left over from the birth of the universe itself. Mixed in were traces of heavier elements, carbon, oxygen, silicon, iron, scattered into space by generations of stars that had lived and died before our sun was even a thought. This cloud just floated there. It had been floating for a long time, in balance. The pressure of the gas pushing outward, the gravity of the gas pulling inward, everything in a kind of slow, suspended peace. And then something disturbed it. Maybe a shockwave from a nearby star that exploded. Maybe the gravitational nudge of a passing mass. Whatever it was, the balance broke. Part of the cloud began to collapse inward. Gravity had won, at least in that region. The cloud began to fall toward itself, and here is the moment that created everything you know. As the cloud collapsed, it began to spin. Now, it was almost certainly already spinning very slightly. Nearly everything in the universe has some tiny amount of rotation. But as the cloud contracted, as it got smaller and denser, that spin accelerated dramatically. If you have ever watched a figure skater pull their arms in during a spin, you have seen this principle. The skater gets faster without anyone pushing them. The same angular momentum, the same rotational energy, is packed into a smaller and smaller space. The spin gets faster and faster as the size gets smaller and smaller. The collapsing cloud did the same thing. It spun fast, and as it spun, something remarkable happened to its shape. Imagine taking a ball of clay and spinning it rapidly. It flattens. The equator expands outward. The poles are pulled in. The spin creates a preference, a direction, a plane. Everything gets organized along that plane. The collapsing cloud did exactly this. It flattened into a spinning disk, a pancake of gas and dust, with a dense, hot concentration of material at the center. That center became the sun. The remaining disk, spinning around the young star, became what scientists call the protoplanetary disk, Within that spinning disk, particles of dust and ice began to stick together. Tiny grains became pebbles. Pebbles became boulders. Boulders became kilometre-sized objects called planetesimals. And over millions of years of collision and merging and gravitational gathering, these planetesimals became the planets we know today. All of them formed inside that flat, spinning disk. All of them inherited the disk's geometry. All of them orbit roughly in the same plane, because they all came from the same flat rotating structure. That plane is what astronomers call the ecliptic. It is defined by Earth's orbit around the Sun. When someone says a comet is 20 degrees above the ecliptic, they mean 20 degrees above this imaginary flat surface that Earth traces out once a year. It is the zero line, the reference plane, the base of all solar system geometry. And for the 8 major planets, it works. They all orbit within a few degrees of this plane. The solar system really is, in a genuine physical sense, remarkably flat. But remarkably flat is not perfectly flat, and that difference matters enormously. Even among the 8 planets, none of them is exactly on the ecliptic except Earth, and only because the ecliptic is defined by Earth's orbit. Every other planet is tilted. Mercury, the innermost planet, has an orbital inclination of about 7 degrees. That might sound small, but Mercury orbits the Sun at an average distance of about 58 million kilometers. At 7 degrees of tilt, Mercury can reach a maximum height above or below the ecliptic of about 7 million kilometers. That is nearly 10 times the diameter of the Sun. Mercury, which the flat diagram shows sitting neatly on the line, is actually ranging millions of kilometers above and below that line during every single orbit. Venus sits at 3.4 degrees, Mars is at 1.8 degrees, Jupiter at 1.3, Saturn at 2.5, Uranus at 0.8, Neptune at 1.8. These tilts are small, but they are real, and they mean the solar system is not a flat geometric surface. It is more like a very thin disk, with the planets wobbling gently above and below the central plane as they orbit, tracing paths that are almost but not quite flat, weaving through space like slow cosmic ribbons. The planets are close enough to flat that the diagram is a fair representation of reality for most purposes. But what lies beyond the planets is where the flat picture completely collapses. Because as you move outward from the Sun, away from the orderly realm of the planets, the objects you encounter have tilts that are not 1 or 2 or 7 degrees. They have tilts of 20 degrees, 40 degrees, 60 degrees, 90 degrees. Some even orbit the Sun in the opposite direction from the planets. And at the very edge of the solar system, in the structure that defines its true outer boundary, there is no preferred plane at all. Objects orbit in every possible direction. Flat becomes meaningless. The solar system at its full extent is not a disk, it is a sphere. But we are getting ahead of ourselves. Let us walk through this step by step, starting with the objects just beyond the planets. You know the asteroid belt. It sits between Mars and Jupiter, a ring of rocky debris that represents material that never quite gathered into a planet, partly because Jupiter's powerful gravity kept stirring things up and preventing the kind of sustained merging that built the other planets. Most of the asteroid belt orbits relatively close to the ecliptic, but even here, the tilts are noticeably larger than the planetary inclinations. While the planets have inclinations measured in single digits, asteroids in the main belt routinely have inclinations of 10, 15, 20 degrees. Some have inclinations of 30 degrees or more. The asteroid Pallas, one of the largest objects in the belt, has an orbital inclination of about 34.8 degrees. Pallas does not stay anywhere near the flat disk of the planets. Its orbit carries it far above and below the ecliptic, sweeping through altitudes of hundreds of millions of kilometers on either side of the plane. If you put Pallas in the standard solar system diagram, it would not be on the line, it would be way off the page. But Pallas is almost never shown in those diagrams. because it does not fit the narrative that the diagram is trying to tell. The flat diagram is a curated view. It shows you the objects that orbit near the ecliptic and quietly ignores the ones that do not. This is how the illusion of flatness is maintained. It is not a conspiracy. It is just simplification. But simplification, when it is never questioned, becomes assumption, and assumption becomes the picture that lives in your head. The asteroid belt is only the beginning. Beyond Mars, beyond the asteroid belt, past the giant planets, past the realm of familiar solar system objects, lies a population of icy bodies that lives in the outer solar system. These are the trans-Neptunian objects, and they are where the story gets extraordinary. The first hint that something strange was happening beyond Neptune came from Pluto. Pluto was discovered in 1930 and called a planet for 76 years. It was treated as the outermost member of the solar system family, the quiet ninth planet at the edge of the flat diagram. But Pluto was never truly comfortable in that lineup. Its orbit was always suspicious, always different, always hinting that it belonged to a different category of object entirely. One of the biggest differences was its orbital inclination. Pluto's orbit is tilted about 17 degrees relative to the ecliptic. That is more than twice Mercury's inclination, which is the highest among the 8 major planets. 17 degrees sounds modest, but remember the distances involved. Pluto orbits the Sun at an average distance of about 5.9 billion kilometers. At 17 degrees of tilt, Pluto can reach a maximum height above or below the ecliptic of more than 1,200 million kilometers. To put that in perspective, 1,200 million kilometers is more than 8 times the distance from Earth to the Sun. Pluto does not wobble slightly above and below the ecliptic. It soars. Its orbit, seen edge-on, looks like a hula hoop leaning against a wall, and it sweeps through an enormous volume of three-dimensional space, spending half its 248-year orbit above the ecliptic and half below it. The standard diagram shows Pluto on the line. In reality, Pluto spends virtually none of its time on the line. But Pluto's reclassification in 2006 as a dwarf planet was not just about its size. It was about what the discovery of other outer solar system objects revealed. Because by the early 2000s, astronomers were finding more and more objects in the outer solar system, and many of them were like Pluto in critical ways. Icy, small relative to the planets, and orbiting on paths that were tilted, eccentric, and unlike anything in the neat planetary diagram. This population of objects is the Kuiper Belt. The Kuiper Belt extends from roughly the orbit of Neptune at about 30 astronomical units from the Sun to about 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, approximately 150 million kilometers. The Kuiper Belt is a vast ring of icy bodies, remnants from the solar system's formation that never coalesced into a planet. More than 2,000 Kuiper Belt objects have been discovered so far. Astronomers estimate the belt contains hundreds of thousands of objects, larger than 100 kilometers in diameter. But what matters for our story is its shape. The Kuiper Belt is not flat. It is much thicker and more three-dimensional than the planetary region of the solar system. While the 8 planets orbit within a disk that is only a few degrees thick, Kuiper Belt objects have a wide range of inclinations. Some orbit close to the ecliptic. Many do not. The overall structure of the Kuiper Belt is more like a thick donut than a thin disk. Objects within it can have inclinations of 5, 10, 20, 30 degrees or more. Astronomers divide Kuiper Belt objects into several populations based on their orbital behavior. The cold classical Kuiper Belt objects, often called cubewanos after the naming convention of the first ones discovered, orbit between about 42 and 48 astronomical units in relatively circular paths. Their inclinations tend to be low, less than 5 degrees or so. They are close to flat, an echo of the original protoplanetary disk. But the hot classical population is different. These objects have much higher inclinations, up to 30 degrees. They were likely scattered into their tilted orbits by gravitational interactions with Neptune during the chaotic early history of the solar system. The fact that two populations coexist in the same region, one flat and one thick, tells us that the Kuiper Belt is not a simple structure. It has layers. It has history written into its geometry. Then there are the resonant Kuiper Belt objects. These are bodies whose orbital periods are in a simple mathematical ratio with Neptune's orbital period. Pluto is the most famous example. Its orbital period is in a 3:2 resonance with Neptune, meaning Neptune completes 3 orbits for every 2 Pluto completes. This resonance acts as a gravitational lock that keeps Pluto and Neptune from ever approaching each other, even though their orbits cross on paper. Other resonant populations exist at different ratios, and they can have a wide range of inclinations. Some are nearly flat, others are steeply tilted. The resonances can actually protect objects at high inclinations from being ejected from the solar system, allowing them to survive on tilted orbits for billions of years that would otherwise be gravitationally unstable. But the most dramatic departures from the flat picture come from a population called the scattered disk. Scattered disk objects are Kuiper Belt objects that have been flung onto highly eccentric and highly inclined orbits by close gravitational encounters with Neptune. While a typical classical Kuiper Belt object has a relatively circular orbit that stays between 30 and 50 astronomical units from the Sun, scattered disk objects have stretched, elongated orbits that can carry them in from just inside Neptune's orbit out to hundreds or even thousands of astronomical units at their farthest point, and their inclinations can be extreme. Eris, the scattered disk object whose discovery in 2005 by astronomer Mike Brown and his team ultimately led to Pluto's reclassification, has an orbital inclination of about 44 degrees. That is nearly halfway to being perpendicular to the ecliptic. Eris's orbit takes it so far above and below the planetary plane that including it in the standard flat diagram would be almost comically impossible. At its maximum distance from the ecliptic, Eris can be billions of kilometers above or below the plane where the planets orbit. It spends most of its 559-year orbit far from the ecliptic, sweeping through a vast volume of 3-dimensional space that the flat picture has never acknowledged. Eris is not alone. There are scattered disk objects with inclinations exceeding 50 degrees, 60 degrees. Some have orbits that take them so far from the ecliptic that they spend centuries at a time well outside the volume that most sky surveys even examine. Surveys of the outer solar system tend to look near the ecliptic because that is where the planets are. This means we are systematically biased toward finding objects that are close to the flat plane. The tilted objects, the ones with steep inclinations, are undercounted. The scattered disk could contain far more mass and far more objects than we currently know about. Stop for a moment and think about what this means. When you think of the solar system, you picture 8 planets in a flat disk. But the solar system also contains, outside the orbit of Neptune alone, at least hundreds of thousands of known icy objects, ranging from nearly flat to nearly perpendicular. The flat part of the solar system, the part with the 8 planets, is not the whole solar system. It is not even the majority of the solar system in terms of the number of objects or the volume of space they occupy. It is just the innermost, most orderly, most visible part. The outer solar system is a vast 3-dimensional cloud of icy bodies that extends in every direction, getting less and less flat as you move farther from the Sun until at the very edge of the solar system's gravitational reach, flatness means nothing at all. There is also a population beyond the scattered disk that astronomers call detached objects, or sometimes extended scattered disk objects. These bodies have orbits so distant that they are no longer significantly influenced by Neptune's gravity. Their closest approaches to the Sun, their perihelia, are far enough out that Neptune cannot perturb them meaningfully. Something else must have shaped their orbits. Sedna is the most famous detached object. Discovered in 2003, Sedna has one of the most extreme orbits of any known solar system object. Its perihelion, its closest point to the Sun, is about 76 astronomical units, far beyond Neptune's reach. Its aphelion, its farthest point, is a staggering 937 astronomical units from the Sun. That is approximately 140 billion kilometers. Sedna takes about 11,400 Earth years to complete one orbit. 11,400 years ago, the last ice age was ending. Humans were just beginning to settle into agriculture, and Sedna, in the outer solar system, was just starting one of its long elliptical loops around the Sun. The fact that Sedna's perihelion is so far from Neptune raises a deep question. What put it there? How did it end up on an orbit with the closest approach so far from the planets? Neptune's influence does not reach that far. Something else must have pushed or pulled Sedna into its current path. A passing star during the solar system's early history, when it was still embedded in a star cluster. The slow accumulated gravitational influence of the galaxy itself, or possibly the gravitational influence of a large undiscovered planet in the outer solar system, which some astronomers have proposed and nicknamed Planet 9. Planet 9 remains hypothetical as of today. Despite extensive searches, no one has directly observed it, but the gravitational evidence is genuinely intriguing. Multiple distant Kuiper belt and scattered disk objects show a clustering of orbits that is statistically difficult to explain without some large perturbing mass. If Planet 9 exists, it would have a mass of roughly 5 to 10 times Earth's mass, orbit at a distance of perhaps 400 to 800 astronomical units from the Sun, and have an orbital inclination of about 15 to 25 degrees relative to the ecliptic. It would be yet another object that breaks the flat picture entirely. But even without Planet 9, the objects we have already found are enough to completely shatter the flat diagram. The solar system is not a flat disk with a few planets on it. It is a flat inner disk of planets surrounded by a thickening cloud of icy objects that gets more three-dimensional with distance, trending toward full spherical distribution in the outermost reaches. And speaking of the outermost reaches, it is time to talk about the structure that defines the true size and shape of the solar system. The Oort Cloud. What lies above the solar system? What lies below it? At large enough distances, the answer is stunning. More solar system. The Oort Cloud is a vast, roughly spherical shell of icy bodies that surrounds the entire solar system in every direction. Above the ecliptic, below the ecliptic, to the sides, in every direction equally. It is not a disk or a belt or a ring, it is a sphere. A cosmic bubble, the true outer boundary of the Sun's gravitational family, and it is enormous. Let us talk about scale for a moment, because without feeling the scale, the Oort Cloud is just a word. Neptune, the outermost major planet, orbits the Sun at about 30 astronomical units. The Kuiper belt extends to about 50 astronomical units. Sedna, at its farthest, reaches about 937 astronomical units. The inner edge of the Oort Cloud is thought to begin at roughly 2,000 to 5,000 astronomical units. The outer edge is estimated at somewhere between 50,000 and 100,000 astronomical units. 100,000 astronomical units is approximately 1.6 light years. The nearest star to our Sun, Proxima Centauri, is about 4.2 light years away. The outer Oort Cloud stretches nearly 40% of the way to the nearest star. Let that settle in. If you took a model of the solar system, where Neptune's orbit is the size of a quarter coin, 2.5 centimeters across, the outer edge of the Oort Cloud would be about 80 meters away from that quarter. You would need to walk the length of a football field just to reach the boundary of your own solar system. and between that tiny coin and that distant wall, nearly nothing would be visible. Just a few invisible specks of ice drifting in complete darkness. The Oort Cloud was first proposed in 1950 by Dutch astronomer Jan Oort. He noticed something peculiar about long-period comets with orbital periods greater than 200 years. When he calculated their orbits backward to find where they came from, he found that many of them originated from roughly the same enormous distance, somewhere between 20,000 and 100,000 astronomical units from the Sun. But more revealing than the distance was the direction. These comets came from everywhere, not from near the ecliptic, like the planets and most Kuiper belt objects, not from one preferred direction. They came from above. They came from below. They came from every angle, distributed across the full 360 degrees of the sky in what appeared to be a random isotropic pattern. Think about what this implies. If long-period comets come from all directions equally, their source must surround the solar system in all directions equally. A flat disk source would produce comets arriving from near the ecliptic. A ring would produce comets from along the ring's plane. Only a spherical source, a shell of material distributed uniformly around the Sun in every direction, would produce comets arriving from all parts of the sky. The Oort Cloud is that sphere. It is the solar system's outer boundary in all directions simultaneously, not just in the ecliptic plane, not just along the flat disk of the planets, in every direction, including straight up from the ecliptic, including straight down from it. What lies above the solar system? The Oort Cloud, stretching straight above, perpendicular to the ecliptic for more than a light year. What lies below the solar system? The Oort Cloud, stretching straight below in the opposite direction for the same enormous distance. The Oort Cloud has roughly the same density in all directions. There is as much solar system material directly above the Sun's north pole as there is along the ecliptic. There is as much below the south pole as there is alongside the plane of the planets. The ecliptic plane, which feels so fundamental from our position on Earth, has no special significance in the Oort Cloud. It is just one plane among infinite possible planes. The Oort Cloud does not know about the ecliptic. It surrounds us equally. The objects within the Oort Cloud are icy bodies similar in composition to comets and Kuiper belt objects. Water ice, frozen methane, frozen ammonia, frozen carbon dioxide, mixed with rocky and dusty material. Most are probably small, just a few kilometers across, similar in size to comets, but there may also be larger objects out there. Perhaps dwarf planet-sized bodies drifting in the outer darkness, too faint and too far to have ever been detected. How many objects are in the Oort Cloud? Estimates vary widely because we have never directly observed a single Oort Cloud object in its natural habitat. Everything we know comes from the comets it occasionally sends toward the inner solar system. Based on the rate at which long-period comets appear, astronomers estimate the outer Oort Cloud contains somewhere between several hundred billion and 2 trillion objects larger than about 1 kilometer in size. The inner regions might contain 5 to 10 times more than that. The total mass of the Oort Cloud is probably between 1 and 40 times the mass of Earth, spread across a volume of space so vast that if you were somehow transported into the middle of it, you would see absolutely nothing. The average distance between Oort Cloud objects is likely tens of millions of kilometers. The nearest object would be invisible, too small and too dark, lost against the blackness. The Sun from that distance would appear as just another star in the sky, brighter than most but not overwhelming. Just a point of light in a sea of other points of light. You would be utterly alone, completely surrounded by darkness, surrounded without being able to see it by trillions of frozen worlds. This is what lies above and below our solar system. Not emptiness, not nothing. An invisible, vast, spherical ocean of frozen debris, orbiting the Sun at such enormous distances that each orbit takes thousands or millions of years to complete. the most remote members of our Sun's family, drifting in the outermost reaches of its gravitational influence, barely held, almost free, just barely not interstellar. Now, the Oort Cloud is not completely uniform. Astronomers believe it has two main components. The outer Oort Cloud, sometimes called the isotropic Oort Cloud, is the spherical shell that Jan Oort originally proposed. It extends from roughly 20,000 to 100,000 astronomical units. The objects in this region have orbits that are essentially randomly oriented. Their inclinations span the full range from 0 to 180 degrees. There is no concentration near the ecliptic, no preferred plane at all. This outer shell is the source of most long-period comets. The inner Oort Cloud, sometimes called the Hills Cloud after astronomer Jack Hills, who proposed it in 1981, is thought to be a denser region between roughly 2,000 and 20,000 astronomical units. The inner Oort Cloud may retain some slight preference for the ecliptic plane, a faint echo of the original protoplanetary disk, a ghost of the flatness that characterized the solar system's birth. But even this inner component is vastly more three-dimensional than the Kuiper belt or the scattered disk. It is a transition zone, a region where the last remnants of the solar system's original flat geometry dissolve into the perfect sphere of the outer cloud. Something is worth pausing on here because it connects to something deeper. The Oort Cloud was not always where it is now. The objects in it did not form there. They were born in the inner solar system, in the protoplanetary disk, as planetesimals and early Kuiper belt objects. But during the violent, chaotic early history of the solar system, particularly during the period when Jupiter and Saturn were forming and migrating, their enormous gravitational influence sent countless smaller objects flying outward. Some escaped the solar system entirely, becoming interstellar objects drifting between the stars. Others were thrown onto enormous elliptical orbits that took them to the very edge of the solar system's gravitational reach, into the vast cold dark where the Oort Cloud now resides. The Sun holds on to them, but barely. At Oort Cloud distances, the Sun's gravitational grip is so weak that even tiny perturbations can dramatically change an object's orbit. A nearby star passing within a light year, the slow differential pull of the galaxy's mass, the galactic tide, even giant molecular clouds, massive concentrations of gas and dust that the solar system occasionally passes through on its journey around the galaxy. Any of these can nudge an Oort Cloud object out of its stable distant orbit and send it falling inward. When an Oort Cloud object falls inward, it spends millions of years on its long descent toward the inner solar system. When it finally arrives, still carrying ice from 4.5 billion years ago, still chemically frozen at the composition of the solar system's birth, the Sun's heat begins to vaporize it. It grows a coma, a glowing atmosphere of gas and dust. It grows a tail pointing away from the Sun. It becomes a comet, a long-period comet, a visitor from the outermost darkness, bringing ancient ice on a brief brilliant arc through the inner solar system before heading back out into the void. This is where comets come from, not from some nearby ring. From the outer shell of the solar system itself, from above, below, and from every direction. If you have ever seen a comet in the sky, you are seeing a piece of the Oort Cloud, a fragment of the shell that surrounds us completely, a messenger from the outermost edge of our solar system, briefly lit by the Sun before returning to the dark. And now, having understood the true shape of the solar system, we need to zoom out one more time, because the solar system does not exist in isolation. It is embedded inside the Milky Way Galaxy, and the relationship between the solar system and the galaxy adds yet another layer of meaning to the question of what lies above and below us. Here is something that almost no diagram ever shows you. The ecliptic plane and the galactic plane are not the same. They are not even close to the same. The flat disk of our solar system, the plane of the planets, is tilted at roughly 60 degrees relative to the flat disk of our galaxy. 60 degrees. Think about what this means. If you imagine the Milky Way as a vast horizontal table, the solar system's ecliptic is not lying flat on that table. It is propped up at a steep angle, like a dinner plate, leaning against a wall. The north pole of the ecliptic, the direction you would travel if you flew straight up from the planetary orbits, points in a completely different direction from the north pole of the galaxy. This 60-degree tilt means that when astronomers talk about above and below the solar system, and when they talk about above and below the galaxies, they are talking about two completely different directions in space. The north pole of the ecliptic points roughly toward the constellation Draco. The north pole of the galaxy points roughly toward the constellation Coma Berenices. These two directions are separated by about 60 degrees in the sky. What does this mean practically? It means that if you travelled straight above the solar system, perpendicular to the ecliptic, you would not be travelling straight out of the galaxy. You would be cutting through the galaxy at a steep angle, like a needle being pushed diagonally through a stack of paper. You would eventually leave the galactic disk, but not by the most direct route. The solar system is, in the sense, tilted within its own galaxy. We orbit the galactic center, but we orbit it at an angle to the galactic plane. We are tilted adventurers, cutting through the galaxy at 60 degrees, carrying our planets and our Oort Cloud and all our cosmic history at an oblique angle to the vast flat structure that contains us. The Sun orbits the galactic center at a speed of roughly 230 kilometers per second. One complete orbit takes about 225 to 250 million years. For context, the last time the solar system was in its current position relative to the galaxy, the most recent common ancestor of all animals was alive on Earth. The dinosaurs had not yet appeared. They would not appear for another 200 million years. We have been around the galaxy once since then and are a small fraction of the way into our next orbit. But the solar system does not just orbit the galactic center in a circle, it oscillates. As it travels around the galaxy, the combined gravitational pull of all the stars, gas, dark matter, and other mass in the galactic disk causes the solar system to bob up and down. When it is above the galactic midplane, gravity pulls it back down. When it passes through the midplane and continues below, gravity pulls it back up. The solar system rides up and down through the galactic disk like a horse on a cosmic carousel, completing one full vertical oscillation roughly every 60 to 70 million years. Right now, the Sun is approximately 50 to 80 light years above the galactic midplane. It is heading upward. In a few million years, it will reach its maximum height above the disk, somewhere around 150 to 200 light years, and then gravity will pull it back down. It will cross the midplane again, continue below it, reach maximum depth below, and return. Over and over. 65 million year cycles of rising and falling through the galaxy. If you are interested in where we are at this very moment in the galaxy, we are in the northern half of the galactic disk, just slightly above center, in a region called the Orion Arm, which is a minor spiral arm or spur of the Milky Way. We are about 26,000 light years from the galactic center, roughly halfway between the center and the outer edge of the visible disk. Not in the crowded, dangerous core, not in the thin, sparse outer regions. In a relatively quiet suburban area of the galaxy, where star formation is moderate, where supernovae are not too frequent, and where the conditions for a stable solar system with a planet capable of supporting life have apparently been just right. Some researchers have proposed that this oscillation through the galactic disk might have real consequences for life on Earth. When the solar system is near the galactic midplane, it passes through the densest part of the disk, encountering more stars, more gas clouds, more molecular clouds. These encounters can perturb the Oort Cloud, sending more comets into the inner solar system and increasing the rate of impacts on Earth and the other planets. Some scientists have proposed a correlation between these oscillation cycles and the timing of mass extinctions in Earth's biological history. The idea is controversial and not universally accepted, but the basic physics of increased perturbation near the galactic midplane is real. What this means is that the solar system's position in the galaxy, including its vertical position above or below the galactic plane, is not just an abstract astronomical fact. It may have influenced the history of life on this planet. The evolution of species, the extinction of the dinosaurs, the eventual emergence of human beings might all be connected in some small way to the slow bobbing of our solar system through the Milky Way. Now let us go even further out. Beyond the solar system, beyond the Oort Cloud, into the space between stars, into the galactic disk itself, and above and below the disk. When the solar wind, the constant stream of charged particles emanating from the Sun, finally runs out of strength, it meets the interstellar medium. The region where this meeting occurs is called the heliopause, and it marks what many define as the actual edge of the solar system in terms of direct solar influence. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed it in 2018. These spacecraft, launched in 1977, are the first human-made objects to ever leave the bubble of the Sun's direct influence and enter true interstellar space. But they have not left the solar system, not in the deeper sense. They are still well within the gravitational reach of the Sun. They are in the vast space between the heliopauses and the inner edge of the Oort Cloud. At their current speeds, it would take Voyager 1 approximately another 20,000 years just to reach the inner edge of the Oort Cloud, and tens of thousands of years more to pass through it completely. This region, between the heliopause at about 120 astronomical units and the inner Oort Cloud at a few thousand astronomical units, is one of the emptiest, least known regions of the solar system. Very little is known about it directly. No probe has ever been sent there with the specific intention of studying it. We infer its properties mostly from models and from the data sent back by the Voyagers as they pass through it. What is out there above and below the solar system in this transitional region? Extremely thin, extremely cold gas. The occasional scattered disk or detached object on a highly inclined orbit. The faint whisper of the solar wind still pushing outward but growing weaker. The beginning of the interstellar medium pressing inward. A vast, almost featureless void separating the dynamic solar wind bubble from the ancient ice of the Oort Cloud. Above the ecliptic in this region, there is, in some literal sense, nothing that has ever been touched by a human instrument. Below the ecliptic, the same. These are perhaps the most pristine, most unexplored regions in our own solar neighborhood. Not the surface of some distant exoplanet. Right here, just above and below where we live. But we know some things about the local interstellar environment that the solar system is embedded in. The Sun is currently traveling through a region of low-density gas called the local interstellar cloud. This cloud is about 30 light-years across and is itself embedded within a much larger low-density region called the local bubble. The local bubble is a cavity in the interstellar medium roughly 1,000 light-years across. The gas within it is much thinner and hotter than the average interstellar medium. This cavity was almost certainly carved out by supernova explosions that occurred somewhere between 10 and 20 million years ago. A series of massive stars in this part of the galaxy ended their lives in titanic explosions. Each supernova sent a shockwave, expanding outward at enormous speed, pushing gas and dust ahead of it, sweeping the local volume relatively clear of dense material. The solar system has been travelling through this local bubble for about 5 million years or so. Before we entered it, the interstellar environment was different, denser, and the heliosphere, the Sun's protective bubble, might have been significantly smaller. Inside the local bubble, with less external gas pressure, the heliosphere can expand more fully. providing more shielding from galactic cosmic rays. There is even physical evidence of our journey through the local bubble written in the rocks of our own planet. Deep ocean sediments on Earth contain elevated levels of iron-60, a radioactive isotope that can only be produced in supernovae, and that has a half-life of about 2.6 million years. Iron-60, that should have decayed long ago, is found in relatively recent rock layers, suggesting it was deposited on Earth from supernova debris. As the solar system crossed the denser walls of the local bubble in the relatively recent past, geologically speaking, the stars exploded. The shockwave swept through this part of the galaxy. Debris from those ancient stellar deaths settled on the floor of Earth's oceans. Locked in the rock beneath our feet are the fingerprints of stars that died before our ancestors were human. This is not metaphor. This is what the iron in the sediment represents. The local bubble has walls, denser regions of gas and dust at its edges where material has piled up under the pressure of those ancient supernova shockwaves. And on those walls, triggered by the compression of gas, new stars are forming. The death of old stars carved a cavity, and on the edges of that cavity, the deaths gave birth to a new generation. So when you ask what lies above and below the solar system, and you zoom out to the scale of the local galactic neighborhood, the answer is this. We are inside a vast room, a bubble of relatively empty space carved by stellar explosions. Above us, extending for hundreds of light years, is this bubble. Below us, the same. Around us, for hundreds of light years, the same diffuse hot gas within the cavity. And at the walls, the compressed denser regions where new stellar nurseries are forming, where new suns are being born, where new solar systems might one day produce new worlds and new questions. And zooming out still further, above and below the galactic disk, beyond the spiral arms and the dense star-forming regions and the molecular clouds, the Milky Way gives way to its halo. The galactic halo is a vast, roughly spherical region surrounding the Milky Way's disk. It extends from the edges of the visible disk outward for perhaps 100,000 light years or more in every direction, including directly above and below the flat plane of the galaxy. And it is made of two distinct components. The stellar halo is populated by ancient, metal-poor stars, many of them among the oldest in the galaxy. These stars formed more than 10 billion years ago, when the universe itself was young, before the galactic disk had fully developed, when the galaxy was still an irregular blob of gas, slowly settling into its familiar spiral form. These halo stars do not orbit in the flat disk the way the Sun does. They move on tilted, elongated paths that carry them high above and deep below the galactic plane, swooping through enormous volumes of three-dimensional space before returning. Some of these halo stars are not native to the Milky Way at all. They are relics of smaller galaxies that the Milky Way consumed over billions of years. When a small dwarf galaxy strays too close to the Milky Way, the larger galaxy's gravity tears it apart. Its stars are stripped away, scattered into long streams that eventually become indistinguishable from the native halo population. The stellar halo is, in part, a graveyard of consumed galaxies, their stars still moving on the orbits they inherited from their original home systems, orbits that carry them high above and below the galactic disk. Globular clusters are another feature of the halo. These are dense spherical collections of hundreds of thousands of stars, tightly bound by gravity, ancient remnants of the galaxy's formation. About 150 globular clusters are known to orbit the Milky Way, scattered through the halo, some relatively close to the disk, others at enormous distances, tens of thousands of light years, above or below the galactic plane. But the stellar halo is only one component. The other component is invisible: dark matter. The Milky Way's dark matter halo is thought to extend far beyond the visible stellar halo, reaching perhaps 600,000 light years or more from the galactic center. This dark matter halo is roughly spherical and contains most of the galaxy's total mass. The visible stars, gas, and dust that make up the beautiful spiral you see in photographs of the Milky Way represent only a small fraction of the galaxy's actual mass. The rest, perhaps 80 to 90% of it, is dark matter, invisible, interacting with nothing but gravity, present everywhere but detectable only through its gravitational effects. Above the galactic plane, below it, and in every other direction, the dark matter halo fills space with its invisible presence, shaping the orbits of stars, holding the galaxy together, providing the gravitational scaffolding without which the Milky Way would fly apart. We know it is there. We cannot see it. We cannot touch it. We cannot collect a sample of it. But its gravity is real and measurable, and the motions of stars throughout the galaxy confirm that something massive and invisible surrounds the entire system. When you ask what is above and below the solar system, and you trace it all the way out, you eventually reach the dark matter halo, the Oort Cloud, the interstellar medium, the local bubble, the galactic disk, the stellar halo, the dark matter halo. Each layer more diffuse, more three-dimensional, less related to the original flat disk of the planets, until finally you arrive at something that has no preferred direction at all. And beyond the dark matter halo, intergalactic space. The space between galaxies is the most extreme environment in the known universe. It is not empty in the absolute sense. There is an intergalactic medium, a thin, hot plasma of ionized gas, stretched across the enormous distances between galaxies. But the density of this medium is so extraordinarily low, roughly 1 atom per cubic meter on average, that for all practical purposes, it is indistinguishable from a vacuum. In intergalactic space, there are no stars to light the dark. There is no solar wind, no galactic magnetic field of any significant strength. There is the faint cosmic microwave background radiation, the afterglow of the Big Bang, permeating everything equally from all directions. There is the occasional gamma ray from some distant catastrophe. And in the very farthest distances, there are the lights of other galaxies, hundreds of billions of them scattered across the observable universe. Each one a system of hundreds of billions of stars, each one containing who knows how many solar systems, with who knows how many worlds. If you travelled straight up from the ecliptic, perpendicular to the plane of the planets, you would first pass through the Oort Cloud, then through interstellar space. Then, cutting through the galactic disk at an angle due to that 60-degree tilt we discussed, you would eventually emerge above the galactic plane. You would rise through the stellar halo, through the dark matter halo, and then you would be in intergalactic space. Looking back, you would see the Milky Way as an entire galaxy, a luminous disk with faint spiral arms, a bright central bulge, a faint extended halo. Our solar system would be completely invisible, one ordinary star among 400 billion, somewhere in the disk, too small to detect from this distance. Looking outward, you would see other galaxies. Andromeda, the nearest large spiral galaxy, about 2.5 million light-years away. The Magellanic Clouds, satellite galaxies of the Milky Way, visible as fuzzy patches. Dozens of smaller dwarf galaxies nearby. And in the distance, in every direction, the cosmic web, the vast network of galactic filaments and voids that constitutes the large-scale structure of the universe. Galaxy clusters connected by bridges of dark matter, separated by enormous voids hundreds of millions of light-years across. This is the universe above the solar system, traced from the ecliptic plane outward. This is what exists in that direction, and here is the deepest truth we have been building toward, the one that the flat diagram could never tell you, because the flat diagram never asked the question. There is no real above, there is no real below. The concepts of above and below are products of living on the surface of a planet with gravity. On Earth, down is toward the center of the planet. Up is away from it. These directions are absolutely real and absolutely consistent from your personal perspective. But the moment you leave the planet, they lose all meaning. In orbit, you are in free fall, and there is no gravity to define up or down. In deep space, there is no preferred direction at all. When we say something is above the solar system, we are using the ecliptic plane as a reference. But that is a choice, a human choice, a convenient one, based on the accident that we live on the planet, whose orbit defines the ecliptic. If we lived on Mars, we would use Mars's orbital plane as our reference, and it would be tilted 1.8 degrees from ours. If we lived on a planet orbiting the star Vega, our reference plane would have no connection to Earth's ecliptic at all.